some of you know him already. Introduced Ivan Rybak. He's originally from Minsk.
Yes, but I never met him before.
Never met in person. Probably.
No,
I mean, you met him in Minsk, but there were many people there.
Yes.
Yes, and he's now working at the Institute of Statistics and Space Sciences in Porto, in Portugal. But we are related for quite a long time actually, because he started, he graduated from the Russian University, Russian State University, and I was supervising his works for some time for third and fourth year, physics, if I remember correctly. Then he also applied to our other PhD back in 2014 somewhere, but eventually went to Portugal, and now he's a researcher there, correct? And he also contributed to the recent Master Grossman because he was co-chairing one of the parallel sessions, specifically on cosmic strings. So with this short introduction, we have now the scene, so like half an hour talk or 40 minutes at most, and then we have questions.
Può venire un secondo, Gabriele?
Sì, un
And we're
attimo.
connected with other internet centers
Okay.
here, so.
Thank you very much for the introduction, and it's actually a very big pleasure for me to speak here because, as everybody said, I guess Pescara in, let's say, non-linear way affected my choice of what I studied at. I will be talking about cosmic strings and about cosmic superstring and superconducting strings as a proof of the high energy physics. I think that this is not very familiar topic for you in the sense that you work with in another area. That's why I will try to make a quite detailed introduction and to describe what is actually topological defects, in particular cosmic strings, and why we need to pay attention to them actually, to motivate all this, like, let's say, investigation. And then I will go to details about the cosmic string evolution, how they evolve, and why we should also go to so-called superconducting cosmic string and cosmic superstrings. And then I will end up with the observational constraints that we have nowadays on this subject. And I don't know how usually you have the seminar, but I'm very, let's say, it would be welcome if you ask questions during the presentation. I think it would be more interactive, and actually I think it would be useful for both of us. That's why if you have any question, just ask it. To start the explanation, what is the topological defects and how actually it works, how they can be produced, it's better to consider a toy model where we have Lagrangian in the following form, where we have a scalar field, phi, and we have Z2 symmetry. Z2 symmetry means that we can change phi for minus phi here, and nothing will be changed. It will be the same Lagrangian, completely the same thing. However, when we consider a lowest energy state solution, then actually they are different. Here we have minus phi 0 and phi 0. There are two minimum, and they are distinguished. If we imagine we have some kind of energy, let's say, well above this hilltop, or let's say high temperature, which is the same, and we don't care about the orientation of the field phi, but we have this potential, then if we start to decrease energy, or decrease the temperature, which is the same in our case when the universe expands, there will be a decrease of the energy, the system will go to one of these minima, to the left one or to the right, to the blue one or to the red. It will need to make a choice of one of these minima. And here we have an example when 2 points, for instance, if we have 2 points that are far away from each other, they are separated on a distance bigger than correlation length, then they don't have to choose the same minimum. They can go to different minima. And one, let's say, we can imagine that one area goes to one minima, and another area which was not correlated with this one, on a very big distance, it can go to another minima. As a result, in a space, there can be different patterns of minima. And they will grow in the following way. And we will have here area with the one minima, the red one, and we have area with another minima, which is the blue one. Since we need to require the field phi, which is like everywhere, it should be a continuous function. We should have some kind of, let's say, transition from one minima to another one, when we go from here to here. And this transition is provided by this line, where we will have area which is stuck on this hilltop. And it cannot go to one minimum or to another. It's really stuck here, and it's, let's say, topologically stable. That's why we call this topological defect, because it's topologically, there is topological stability that does not allow this defect to disappear easily. And here we have this line that represents the separation between two minima. But if we go to the third dimension, it will be a surface, which will look something like that. This is a field theory simulation where the field evolves, and all this surface, it represents the field that's stuck on this top of potential. And here, like how the evolution can be happening. And example of this evolution is shown, let's say, in this is supposed to be a video, but you can always go to this YouTube, let's say, YouTube channel, and then you can see the real video of evolution of the main walls, how it evolves, disappear. That was master degree, nothing else. It's a small simulation, but it's publicly available, very useful demonstration. I demonstrated how the domain walls can appear. They call domain walls. They have the surface of the energy. And now what about the cosmic strings? Well, the story is very similar. However, now we have not a real field, but a complex field. And if we have a complex field here, it's, let's say, this Lagrangian is invariant under E1 symmetry, meaning that we always can multiply phi by the exponent in the imaginary power, and the Lagrangian will stay the same. Here is the Barrett-Mix complex conjugate. The Lagrangian stay the same, but the lowest energy state, which corresponds to this potential, will be this circle. Here we have imaginary part of the field and real part of the field. And this circle is represented here. This is the minimum of energy, let's say. And now, using the similar argument that in space there can be different points, they can choose different minimum. Here we have 1, 2, 3, and 4. If we have this configuration that made this circle of minimum, then in the middle, inevitably will be a point that's stuck on this top of potential. And here we have, if you have x, y direction, then we put the z direction, and then this point will be a string-like, well, it's topological defect, this string, and the energy that corresponds to this defect, it will be here, stuck on this top of potential. And it cannot decay, it cannot disappear, unless unless it will be the form of the loop. Here the video which is supposed to demonstrate the cosmic string formation. However, because of some difficulty, we don't have it, but you can always go to this website and see it. Well, the symmetry breaking that I was trying to explain, and hopefully it was more or less clear. It was originally in condensed matter physics, and especially in the famous Ginsburg one-down model applied. Then it went migrated, I would say, to the particle physics with the Higgs mechanism. And eventually, actually, people found that there is a big consequences of this symmetry breaking can be for cosmology. And in particular, Zendorich pointed out, together in the paper with Kobler and Opping, that if the discrete symmetry happened on the early universe, then these kind of defects, which will be domain walls that I was demonstrating in the first slide, they will start to dominate on the universe, and they will actually, well, this is unrealistic, we don't see domain walls. And which is why it means that we cannot have a discrete symmetry breaking on the early universe for some model. Later on, 2 years later, Tom Kibble actually classified and studied in details formation of all possible defects which can exist in general for three-dimensional space. And here we have, and he gave also a mathematical description of this thing. If we have some kind of unified theory or something like any kind of theory which has a symmetry J, and then it's broken to some subgroup K, then if we have, if homotopy group, well, in that case, 0 is like set, homotopy set of this equation space of the group to subgroup, if it's not trivial 0, 1, it would be a formation of walls. If the first homotopy group non-trivial, then it would be strings. In general, we can just take the sum theory, see how the symmetry breaking is happening, and see if we have in this theory some production of topological defects. This can be applied for any kind of configuration of field.
Sorry, just to remember, which would be the main motivation to assume a Mexican had potential of the field in the early universe?
Yeah.
Why it should be there, this kind of potential?
Yeah, I will go to this a bit later. I mean, now I'm just talking about how it was, let's say, initially. Initially, they thought, okay, if there is a unified group, like for instance, S of 10, or then draw away when the symmetry is broken up to the standard model, because it's not necessarily should be like this Mexican potential. Then when we go to standard model, there will be a process of symmetry breaking, which actually will lead to one of these defects, and I will demonstrate in more detail some of these examples, but more often we will see this kind of strings defect. And at that point strings, cosmic string became quite popular, and one of the popularity, let's say, appeared due to the fact that when cosmic string interact, here should be also the video, you can see it here on archive, when strings intersect with each other, they create a loop which eventually collapses. And when this loop collapses, there was the idea that maybe the collapse of this loop will be a seed of the large-scale structure formation. However, when we now study CMB anisotropy, here the CMB from the cosmic string, which we can calculate now quite well, and here what we see in reality, which means like cosmic strings are not the main source of the seed that leads to the formation of the large-scale structure. And at that point, sort of the interest in cosmic string went down. However, as it was asked,
yeah. So to my remember, this was really the main observational kind of rejection or for the community of this as alternative to
the inflation.
Yes.
Yeah, this was exactly like, as you saw, it was 76 when the, well, let's say the paper about topological defects appeared, and in 79, I guess, the inflation Tarobisky model appeared. It was later, and then it was like a, let's say, fight between two ideas. But the CMD exactly clarified that inflation, of course, was the one who was responsible for the seeding, like let's say, the large-scale structure formation, not the loops. And yeah, we sort of don't have some kind of observational evidence that we need to explain. And as it was asked, do we really have this Mexican head potential in the early universe? And apparently we have. All the time, when there is extension of the standard model, we actually end up with the formation of the cosmic strings. Well, not all the time, but very often. Here are some examples. For instance, if we want to explain a neutrino mass, we use the seesaw mechanism, so-called. And for the generation of the dynamical generation of the right-handed mass neutrino, we actually end up for the formation of the cosmic strings. Like if we dynamically generate the right-handed neutrino mass. Also, the resolution of the strong CT problem in QCD, H-plane theory, it also leads to the formation of the cosmic strings. As well as, for instance, in supersymmetric model, which are on the GATT scale, which includes the hybrid type of inflation by genesis, which is with a consistent proton line, with no monopole problems, they unavoidably lead to the formation of cosmic string. All these like using models here. Here an example, for instance, one of the clear example, I guess, of the symmetry breaking, which can be happening. And the paper, which was considering the leptogenesis in the early universe. And here they have some examples, which actually also lead to the many, let's say, scenario where the cosmic strings are produced. Here the purple blue one. And one of the, say, another motivation that also appeared, eventually when people started to apply string theory to the cosmology, and they wanted to make an inflation, One of the candidates is now is the big problem in the string theory to have inflation, but still valid candidate is the brain type of inflation. And actually, in that case, we have the fundamental strings in the string theory. They can be mixed with these strings, like Dirichlet strings, and these kind of strings they will evolve as the cosmic strings as well. And well, Tom Kibble, actually, there is a quote of him that he said that string theory cosmologists have discovered cosmic strings lurking everywhere underground, which tells that all the time when we extend the standard model, when we include something, very often we end up with these defects. And also just to give some motivation, because now it was all like theoretical discussion, here I want to show that actually we already see laws in cosmic string and monopoles, but not in the universe, but in the condensed matter physics. Here are examples of which exactly the same, let's say, idea, the same principles, which lead to the formation of laws, strings, monopoles in condensed matter physics. And here they are like their photos, you could say. Back to the cosmology. As I said, there are some high-energy physics scenarios that lead to the formation of these topological defects, in particular the cosmic strings. They can evolve, and then nowadays we want to observe them, or we want to see some evidence if they are present. If they are present, then okay, we can select some kind of theory where they exist. If they are not present, then we can say we can rule out theories that are extension of the standard model, just based on the fact that there are no cosmic strings. And we just need to be able to distinguish the universe with strings from the universe without strings. This is the main point. But to connect two of these point production and observation, we need to go through all this evolution. We need to understand how they evolve in order to have a clear and precise prediction of the observational signal. Here, a bit more equation, and which actually, if this is the Abelian-Higgs model, the symmetry breaking again, but now instead of U1 it was like before, just simple one. Here this is the gauge U1, let's say, whereas alpha is the local now function, which depends on the coordinate. Here we have the vector field, scalar field with the covariant derivative correspondent, and the same Mexican potential. This is an example, one of the ways how we can actually understand the evolution of the cosmic strings. We just take this model and we put on the computer, we discretize the dynamic of this equation, we put periodic boundary condition, and we try to evolve. And there is one, well, actually one quite big problem. The cosmic string that I produced here is usually very, very tiny. It should be on the size of the proton. However, the length of the string, it can be through the whole observable universe. As a result, we need to make a simulation that simulates observable universe and resolve the very small time in this cosmic string. Well, we need some tricks to allow this simulation to resolve this cosmic string, and that's why we must have to make a growing string core and some like additional tricks in order to be able to resolve it. Here an example of the simulation for the, let's say, critical coupling. And here when you have this simulation, when you see the field theory, usually you should remember that there are some additional tricks that allow us to resolve. And maybe some physics actually, we sort of, when we start to make strings thicker, we actually get rid of some important physical phenomena. In order to have a better resolution and in order to not lose the, let's say, some information when we make the string fatter, there was another kind of way to make a simulation. We just make the string infinitely thin. We use Navier-Stokes action. Here, as we have particle, we like in a relativistic physics, we can describe particle. Here's the description of one-dimensional string that gives rise to the wall sheet, and mu, the parameter, which each was just integrated out all fields of oscillation of the string, and this is mu. It's a tension for mass per unit length. It tells how much energy we have per unit length on this object. And in that way, we can make a very nice simulation with a lot of details. But now we simulate not a field, but just let's say just a real strings. And also we lose some physics. Another way to approach this problem is to make a sort of a semi-analytic approach. to make a thermodynamical description. We use this Bogota approximation, then we obtain microscopic equation. And then we average them over the volume. And we introduce macroscopic parameters. One of them is RMS velocity, which means square velocity. We say, in average, how the network moves. And we introduce the characteristic lengths, which tell us the average distance between different strings. And then we can have the connection with the density, how much actual density is given to this cosmic string. And this system is actually closed. We can also add here different terms. Here, the term responsible for the loop production. We can add the terms that are responsible for radiation for cosmic strings. And we can sort of like play and understand better the evolution of the cosmic string. What is important is that this model actually predicts quite well what we have in simulation. If we have a scale factor of the universe, like this function of the universe is proportional to the power of time, in that case we should have a scaling solution, so-called. In that case, velocity means the average velocity of the nebula will go to the constant. And the characteristic length of distance between strings will be proportional to the time. Well, and the simulation and this semi-analytical approach, which is called VOS model, they agree very well. And what is important, they also show that independent, if we start with a different velocity, all the time we end up with the same velocity, which means that this solution is attractive. The same for characteristic length. If we start with different initial condition, all the time we end up with the same initial, with the same final network. And okay, we simulated cosmic string, we described it, and everything is nice. However, do we really make a prediction for something realistic? Because before I was showing this picture, and here we have a lot of different fields that interact in a quite complicated way. And the question is, when we just take out a particular realization, like just a particular field that form a cosmic strings, we just neglect all other interactions. And do we really make a prediction for the realistic scenario? And I would say that not exactly. And first who pointed this out, it was in the work of Wheaton, who consider cosmic superconducting strings. Here you have two scalar, here just exactly another model example, where you have a field phi, scalar complex field sigma, and two vector fields. I mean, it's just U1 cross U1, nothing very complicated. Let's say with a potential in the following form. In that case, if we have two fields now interacting, we can have the situation when the string will be formed, and it's formed by the field phi, and the sigma, while it's trivial everywhere, it will be non-trivial, and it can be propagating along the string, and it will be making the string superconducting. And well, we can ask, is it realistic? Is it something like what's going on in reality? And in order to understand this, there were a lot of cases studied, and it was shown that if there are fields that couple with a field that form a cosmic string, there can be a fermion that trapped in this cosmic string. Cosmic string from using models, there can be a vector flux, non-abelian strings, also some current generation. And in particular, if we take the axial strings, which I guess nowadays is quite popular, especially trying to explain the dark matter, using the axions produced by axial strings, they also should be superconducting. There also should be a current that propagates along the strings. As a result, well, probably we should not trust this simulation that just evolved just a field that formed the cosmic string, but we should evolve something more complicated, all this interaction. However, to make simulation, as you already saw, even for the simple cosmic string is complicated. And there are any simulation that can take a realistic scenario. However, we can approach this problem with a semi-analytic model. And first of all, we need to start with Lagrangian, some kind of effective description. As I was telling, the Lagrangian can be for the infinitely thin string, this part. And now here we have additional part which tells us how the current propagates on the string. Well, this was suggested by Wheaton initially, but then it was studied by the Peter Patrick and Brendan Carter in a lot of details, and they ended up that actually effective Lagrangian should look like this. Well, it's quite complicated Lagrangian, let's say. And then let's not limit ourselves, let's just say that we have some action, which is just depend on this function kappa. And let's try to build a model for this general Lagrangian, the same DOS model as it was done before. Now it's much more complicated. We again have this average distance between strings. Again, we have argus velocity. And two more variables we have space-like and time-like curve that exists here. However, here, like, there was a small phi before. Now it's transformed to big phi, which represents the same function. And here, what is we call like charge velocity dependent one scale model is like extension of the standard strings, and it allows us to include this superconductivity of the strings. Well, to let's say to understand this system of equation, quite complicated task. However, for the linear model, now we started that in case of there can be a case for the radiation epoch domination when we have expansion rate proportional to the power of 1/2, then we can actually have two kinds of scenarios. One scenario, we go to the usual model, this is a phase space, where we have the average distance, this is the charge, this is the velocity, and then if we start close enough to the number but limit, we go to the usual strings. Actually, the charge disappears completely, and we recover what initially was, and we say, okay, in that case, we have the model that was before, and everything was simulated correctly. However, if we start with the initial condition, which is close to this point, to the charge string, then actually we can end up with a string network, which has a charge on a radiation epoch, and when it's going to the domination, to the meta-domination epoch, the charge disappears, and it's like evolved as the usual string. However, here we see the very big dump.
So, in that second case, it will affect the radiation, the contribution to the radiation energy in this epoch. If you contribute to the standard radiation.
Yeah, well, the contribution will be, of course. However, let's say the one probably is far away, but there was an expression which was given the energy density, which was the tension divided by the L square. L square is the distance between strings. And in reality, the tension is quite a small value. I will go to the observational. It's for sure less than 10 power minus 7, that's we know for sure, tension. And that's why the contribution to the radiation will be quite small. And it will not change the evolution of the universe by itself. However, here we just say that, okay, if we have charge, then the network with the charge will be evolving, it will be like moving in average, not so fast, but it will be moving slower. And this is like, if the network evolves in a different way, then the whole observational data that we are predicting, they will be different. And here, then I will talk about this in observational part. And another kind of beast that we have is cosmic superstrings. Well, as I said, initially it was coming from the brain type of inflation. The main property is that we have fundamental DRFS strings, and if before strings were interacting and they were exchanging their ends, here, two strings, when they collide, they can create a new one, a green one string, like let's say the blue one is the fundamental string, the red one is DRFS, and they can make this kind of Y-like junction, which can grow, can decrease, and now we don't have so many loops as before. Now the dynamic of the whole network should be different. To evolve this kind of configuration is quite also challenging task. There was some simulation with the toy model. However, we can include this through our semi-analytic description, which is the VOS model. And we can simulate here, it's like the blue string, red string, and the green string. They have different tensions. The heaviest one is the green one, in the middle is the red one, and the lightest one is the blue one. And here we can evolve them, and we can have a velocity for each type of the string, and the density. And the density of this kind of string. That's how the density will be evolving when the scale factor proportional to the power of time. And here we included the dynamics of this Y junction and all kind of like interaction that should be, try to make it as realistic as possible. In addition, just one more statement about this. there was also a claim that this cosmic string, when they create a junction, they can be also superconducting. I mean, we include two of these properties. They can create this wide junction, and they can have also a current that propagates on the strings. And there was a claim that actually we cannot describe this kind of configuration with number approximation. Well, we demonstrated that actually we can. We can describe, and we demonstrated that if we have this velocity, this angle of the collision of the strings, then this would be a region where the third type of the string formation is allowed. It means two strings collide, we form the third one, and it's all allowed on some particular velocity or some particular angles between strings. And this is actually exactly what we anticipate for the axial type of string. They will be superconducted, and there is a possibility that the wide junction can be created. You can see the details in this paper. Now, as we discussed, like all this, let's say, evolution, how this cosmic string could have evolved. But now, what about observational data? Exactly, what it will influence, like what it will change for us, how we can observe. One of the simplest ways to observe it, which was predicted quite a long time ago, is if we have some object, like let's say galaxy, and we have a string between us and between this galaxy, then there will be a lensing appeared, and there will be a deficit angle that is connected with the string tension. As bigger the tension, as bigger, of course, the deficit angle. And instead of one object, of course, we will see like two objects. And this actually was the picture. It was in 2003, measured by a team of Sargent. And they thought even that they actually saw the cosmic string, but eventually it was two galaxies that were very, very similar. And it looked like, first, like it was a legend of cosmic string, but in reality it was just very similar galaxies. And they managed to resolve that actually it's not a cosmic string, and it was a false alert, let's say. However, with this method, when we look on like different galaxies, we try to see the lensing, we can make constraints on the cosmic string tension, which tells that it should be 10⁻⁷, which tells that if we have a symmetry break that produces cosmic strings on the corresponding energy, which corresponds to the string tension, then, well, let's say we can rule out all theories that have a symmetry break that produce cosmic strings with a larger tension than this one.
The lensing there should be, because the string is very thin.
Yes, it's
So
very
it should be kind of micro lensing.
well, yeah,
So it's not due to extend the big object like with lensing or strong.
yeah, it's not. Actually, if we write down, let's say, if we linearize the metric, if we just solve like GR, we put the cylindrical object like this, and then we start to solve GR, and we linearize, we say that mu is very small, and we see that it's quite small, and then we obtain actually the metric around this cylindrical object is exactly as the Minkowski space. However, the angle is changed from 0 to not to exactly to 2 pi, but to smaller. It means that, yeah, it's like actually conical defect on the metric. It's even not like that because of the extended object, just exactly because it's very thin. Very thin, but very concentrated energy in this thin line.
There was recently a paper by Sargent and I mean, last year, and they were reporting some possible string candidate in the
on CMB, yeah, they were also making on the CMB. They were putting, let's say, now that was with the galaxy, but on CMB we can do the same. We can try to see that there are like a single fluctuation, and maybe there is lensing. Yes, there were some candidates for this kind of thing, but none of these candidates still like is confirmed as a cosmic string. That's why we cannot make any claim of the existence. Let's say. However, yeah, we can speculate on and of course, the cosmic microwave background is a very good way to restrict the tension that can be on this object. And again, we use different methods. If we use like temporal simulation, there is one restriction. If we use field theory, there is another, like semi-analytic is like, but all of them in that case, they are very similar. They are like around 10⁻⁷. And this is like telling us that, well, it seems we do something quite correct because with different methods we obtain the same thing. However, if we go a bit like further, if we go to cosmic string which has a bit more, let's say, unusual property, to a so-called type 1 cosmic string, when the mass When I was showing some Lagrangian, there was a mass for the vector field produced and the mass of the scalar field. And we can actually tune to this mass and to make a type 1, let's say, cosmic string that will be in agreement that cosmic string can actually be on the scale of 10 power minus 6. That's why we should be very careful when we say, okay, we restrict some model, but we should be very careful which kind of cosmic string is produced. If it's like this, well, we cannot actually restrict it, it even goes to that scale, and we cannot have restriction. And with the superconducting cosmic string, it's quite similar. Here we just demonstrated that if we have a superconducting current propagate along the string, that actually it can reduce the CMB contribution, mainly just because the string network starts moving slower and slower, and the contribution is smaller and smaller. As a result, we should be very careful with the constraints that will tell which kind of string we really constrain. And one of the best prop, of course, is gravitational radiation. And there was recently some nanograph paper from nanograph which was claiming that they detected some kind of stochastic gravitational wave background. It's a wave background the same as anisotropy, but it consists of gravitational wave. And nanograph claimed that seems like there is some kind of signal, which is not still yet confirmed, but it gave rise to a lot of speculation already how to explain it. And there were papers that were claiming that, well, we can also explain it with the cosmic strings, which actually tell us that, yeah, if it's induced by the cosmic string, we expect to see some other parts of the stochastic gravitational wave belong to the future gravitational wave telescope. And there are missions that are going to be carried out that are going to clarify the situation. One of these missions is the LISA, of course. It will be like the 3 satellites on the orbits of the Earth, which give us a very good constraint on the cosmic strings, and also the pulsar time array with the SCAR. It also gives us very good restriction, but it still needs a lot of time to accumulate the statistic about the for the gravitational wave constraints. However, here we have a very big disagreement in models, actually. Even in an above approximation, when there are people make a simulation, there are, well, let's say, several orders of magnitude disagreements about how to constrain cosmic string. And for now, I would say that when you see some kind of paper that maybe constraints on the cosmic string by the stochastic gravitational wave background, we should be quite careful. I would say that there were 3 types of the model that was looked by this collaboration. And, well, at least the third one seems like not very viable, that was shown in these papers. But, I mean, the progress is good, and maybe in the future it will be clarified what exactly is the correct one. However, again, if we go to something more, let's say, general one, if we put on the cosmic string the current, then actually we can decrease the stochastic gravitational wave background by a lot, quite a lot. In case of the chiral string, there were some papers, and now we just, it's still work in the process. We actually demonstrated that if the current is quite huge, then actually it makes the string quite smooth, and there are no oscillation that produce the gravitational wave background. If it's a loop that's supposed to oscillate, then actually for the big current, it can go to the so-called bottom, to the loop that does not oscillate, and there will not be a radiational from this kind of defect. That's why, again, we should be very careful when we say, okay, we restrict cosmic string, but which type of the cosmic string? And here I would like to finish with the 2 main messages that I would like to give. It's first of all, defects, they really help us to understand the high energy physics. If with the colliders, we can study the energy from the, let's say, going from small energy to the higher energy, here, by topological defects, we can actually study the symmetry breaking mechanism that goes from the high energy physics to the smaller one. As bigger the symmetry breaking, as it corresponds to the bigger energy, as bigger the observational signal is supposed to have. That's why here we can put some constraints on our understanding of high energy physics through this topological defect. However, again, when we make some, let's say, prediction for the signal, we should be very careful which kind of cosmic string. Is the cosmic string which can have a current, or is it the cosmic string which is supposed to have some Y kind of junction? And if it is, then we should take this into account because it changed our prediction quite a lot. thank you for your attention. I hope it was a little bit clear. And if you have more questions, I'm very welcome to answer.
Maybe let's see questions from people. In the meantime, Carlos, please ask.
Can you go back to the former slide of the comparison with the LHC? So, yes, I have always a question or concern is that which is the initial time or the time in which the symmetry breaking happens and you go through one of the meaning of this Mexican hat? Is what a blank era or
It depends on the model. I mean, of course, initially, because imagine we have some kind of symmetry group, and then we break symmetry on some scale, but we cannot, by the model, we can say, okay, it's happening like on this energy scale, or smaller. Like, as well as we talk about supersymmetry, in which scale supersymmetry might appear. Is it like, should it appear somewhere here on LHC, or maybe it's much, much higher? That's why it's really model dependent. But we can just say, okay, if we need something on the high energy pieces that can explain some phenomena for now, but we don't see cosmic string from them, then this model is not viable. We can get rid of it. That's why it's a model dependent thing.
Okay, because if the initial time is for very high energies, let's say, much larger than the TeV, then what with my concern is that you are completely ignorant about the theory there, the Lagrangian, because it has to be a extension of the standard model, and then you don't know this extra term. So you are guessing, putting, for example, a U1 extended to symmetry, etc., or other, and then you are making some taking the consequences of this theory, but you started from something that you are completely.
Yeah, I mean, this is completely right. I mean, the thing is that we need to extend standard model. I mean, there is no way almost to have it like that. There is no way going to have it like this. We need to extend it. The question is only how we can limit this extension. And one of the ways to limit it, like we can use these cosmic strings to limit actually exactly which extension we can have, which extension is viable.
That's why you mentioned roots, for example, the criteria.
Yes.
You have many possible
Yes.
effects depending on.
Yeah, depending on symmetry break and depending on how the groups appear.
Oh, yeah. So unless there is no other independent way to see this, it's difficult. Yes, okay, you can constrain, try to constrain from CMB or anything or whatever.
I don't know, like, I guess there are different methods. I mean, of course, different approaches, maybe like exactly with the CMB, and I guess there is like a lot of probabilities, CMB correlation, like bootstrap method. Yeah, we can like extract information. Here is just one example. How we can do it, and well, I think it's quite effective.
Okay, I have a very basic question. You say now you have a domain, different from usually homogeneous, okay? Now you have domain and the domain world.
Yeah.
Okay? So, question is, I want to learn is, what's total energy? Give you judgment. The stable configuration of this space-time is built by domain and this domain world. Because domain world, you need to have more energy to build. Because in domain, you have energy density. Normally, what do you know? If it's all space-time is homogeneous, means only one domain. And now you have domain and domain world, and many domain and many domain world. It costs energy to build a domain world. So, what do I learn? What kind of stabilization condition you can have for such domain structure? Question one.
What kind of
Energy. Okay, one. If you finally stabilize, what side of domain? Or in the other word, what side of your cosmic string?
Yeah. Let's say that first of all, about the energy. The energy comes. I mean, we have the very high universe somewhere here, and there was like a lot of energy. And let's say some part of this energy, it just topologically stuck on this domain. It just comes from here from here, and it cannot disappear after here if this cosmic string or topological domain walls, if they exist. This is the energy that comes from this Barlow universe. And about the configuration, which is like can be like a stable, let's say. I would say that since actually this kind of things like cosmic strings and domain walls, well, if you take a domain walls like just a straight surface like this, that separate the universe, well, it will be stable. It will not radiate. It will not collapse. It can be the whole size of the observable universe. It can split like the whole universe, and it will be like stable in some sense. However, well, we understand that this kind of domain wall, it can be a straight cosmic string like this through the whole universe. However, the cosmic string cannot have the end. It should be always a circle like it. And it should be always closed somewhere maybe not in observable universe even, and it can be closed there. And well, then eventually if it's closed, then it will be, because of the tension, it will be shrinking. And that's why there is no, like, let's say, in a way of stable configuration that we just put topological defects in some way and they don't collapse. No, eventually they will be collapsing, they will be disappearing. If we form like a loop on the string, it will be disappearing, shrinking, and disappear completely. However, the process will be taking like quite a lot of time. It's not something easy to get rid of. And that's, yeah. And about like if we are talking about the distance, what we anticipate one cosmic string at least per Hubble volume, at least, and that's, let's say, from the quite simple point of view. If we have two uncorrelated points, then here we can anticipate on this distance we can have a cosmic string, which is the Hubble volume. Did I answer your question?
I think this question was if you take the energy budget of the universe, how much energy is in
very small.
It's very small, I mean, because the size is
It's
very tiny.
the density is very big because it comes from here. However, since they are very small, the size of these defects can be close to the size of the volume.
What I try to say, all you discuss, you need to compare the space-time without domain wall. If this energy is positive, then the space-time without domain wall, then you need to argue for some reason it doesn't decay, it's stable. For topological reason, I don't know. I don't see this discussion. All you see the potential is in free space, means local, one space-time. Then you go to all the things. So my question, you see, I just see the Feynman lecture. He discussed the magnetic domain. Magnetic domain. You know magnetic domain. So in a small, high temperature, you have the size of magnetic domain, and so on and so forth. He discussed this. So you build a domain and domain wall. It costs energy to do it. So it is stabilized. How you change it? Okay, I don't go to bigger. Just I don't see this discussion means from total energy point of view.
Yeah.
How this is stabilized against the flat space, not flat, without domain. One. And if it's stabilized, maybe only one cosmic string, only one, maybe, I don't know. It's the size of the universe. So I want to see how you get out this. There's some.
Like in condensed matter, let's say, if we have this domain with a magnetic field, we have some, let's say, material where we have a high temperature, and then we start to decrease temperature. And then the formation of these defects start to, and then the formation of defects start to, I mean, they start to appear, defects. When we, from the high energy, we go to the lower energy. Yes? Yeah? I mean, if you agree with this.
This is an analogy, okay, yes.
Yeah, no, but this is a very good analogy. When we go from the high energy to, from the high temperature to small temperature, on the condensed method, the defects start to appear. They can appear randomly. Like the configuration can be also random, but we anticipate that on the correlation distance, let's say two of these points, they are not correlated with each other when the signature breaking process is happening on some temperature, like critical temperature, when we cross it. Then on this side, we're supposed to have a domains, magnetic domains, and when we decrease the temperature, these magnetic domains, well, in condensed matter they will not evolve so freely as here, they will do like some kind of friction and so on. However, this is like the same analogy. We have the universe, which was very hot, with a very high temperature. Then the same as in condensed matter, we decrease the temperature, and defect forms. And we cannot get rid of it so easily. The same as in magnet, the same as the magnet domain. Yeah, the energy comes from here, from the universe, from the initial point. But the energy here, it's of course it's quite small compared to the whole universe because it's tiny and so on. If we compare the condensed matter physics, I'm quite sure that the energy budget will be quite more in this magnet in the domains, because let's say the interaction is quite different for the condensed matter physics.
There are other questions?
No.
If not, I would like to go back to the first slides you were showing.
The very first one.
No, slides. That next. Forward. Next after this, next, to the larger, next,
Here, this one.
here.
Okay.
Shishen, where are you?
Here.
I think this occasion to express my concern. Not about this work specifically, but more generally. I mean, all this stuff was conceived with, for example, explaining dark matter, scalar dark matter, to check if in the laboratory organization. They both trained years and finally in the laboratories this year. But to me, what strikes me is that they write the equations, then they look for a particle which should be dark matter in the transaction. But now the game is different. The game is profoundly different. Because now this equation, the Lagrangian, the scalar field, the massive scalar field, the interaction of the scalar field and quadratic, the F mu, and the other definition, they are applied not for the one particle dark matter in cosmology, not in cosmology, in the detector of gravitation. They have in mind one particle. But here the game is very different. It's very different. We are speaking about the universe. It's very different. I mean, Mr. Kibble was working at CERN, and they even gave him the Nobel Prize at CERN, where the particle interaction was done. And now we have reached even the field true, which is the depth in cell. Okay? But I have to make a dimension tomorrow, and I take the occasion to make it easy. We don't work about the universe only. We work also on gamma ray burst. And gamma ray burst, we have not the derivation of the accelerator of cell. I mean, we have an energy 10 to the 20 times bigger, 10 to the 30 times bigger gamma ray burst, and energy all the way up to 10 to the 20 electron volt, more than the 10. We have that. We are working here in this place on this. Therefore, I'm concerned about the analogy. You can consider a particle. It's okay?
1 second,
I'll wait for you. You can take a particle and continue to work on a particle. But if you are in or you can take an analogy with the model of a magnetic field and so forth, okay? You can do that. But it's not clear that this applies to a system. And I would like to, it's important to have the presence of you have to apply all this discussion. If you want to make explanation in cosmology, not to a particle, not to a particle itself. No, you are interested in the structure of a self-rotating system, which is the universe. And in particular, you don't know if you have to consider the entire universe, or if you can consider some region. Finally, you follow Sheshem, some region which are finite. But the minimum thing that you have to do is to wonder. General relativity. Because the self-clarity is essential. Now you can say, okay, you can keep working on a single particle, or you can work at of a magnetic wall and zinc. Yes, you can do that. But you are now playing a game much more delicate, because you, sorry to repeat, you also for the Chinese student, you are speaking about the universe. And the one thing certain that we know is that the universe is self-rotating. This was said for certain. Now, you don't know, we don't know, if there are condensation due to self-gravity. We don't know the size of the self-gravitating system we are considering. But the certain thing that we have to know is that there you cannot take away without the justification that Lagrange should, since you are speaking about large mass and so forth, should not have an Einstein equation that
Can I
no, excuse me, I would like to finish first. Okay? Now, for the case in which we have a scalar field, which is, you add the general relativity, F mu is there, the second term in scalar is there, the third term is there, the quadratic term is not there. But this was solved long ago in, you can look, the self-gravitating bosons. And there are completely different solutions, because some gravitating bosons can create a black hole, can create a lot of things. Therefore, it's not a question of going into detail, but in the moment that you consider this thing and self-gravitating and creating something, I think first look at for that string the equation for the effect of general relativity. Of course you can say it's zero. No, you have to solve, at least the Rybak can explain, but you have to solve some estimate of this. And to show that there are no other solutions which are completely different due to self-gravity. This is just a comment and an invitation to you to go and look my own work. It's not because I wrote, but I really think this has been one of the most important papers I've ever wrote, the boson self-interaction, and people should think keep going. Wherever they go, they can go, keep going, and so forth. But now we have also the possibility to check not only like CERN, much better than CERN. I made two statements here. One is the role of self-gravity in this theory. And second, the fact that we don't need CERN. We can work very well with high energy astrophysics because we can explore much more than CERN. And with huge flux. Okay, these are two remarks. Different.
One related comment about his comment is that maybe to put in other words, or like the question is it possible to solve taking one of these fields, scalar fields that then generate the string? Is it possible to put in the G union and then make the cosmological perturbation theory with this extra field to see how structure grows in a prima order universe with lambda, with the matter, but also with this? It has been done, because in that case, you will start to see the effect of this field in the structure formation.
Yes, but what I'm saying, you can do in a cheaper way to consider
Already relaxed.
on a piece, a self-gravitating system. And if you find formation of horizon and so forth, please go slow down. Slow down.
Yeah, actually, just some comments. For instance, if you say like resistance, you mean put perturbation of the field on the, this is not perturbative effect. I mean, this is not what we can start with like perturbation theory. But if we take as the sum of the Goromity, we can actually study. And, I didn't mention it, but yeah, for instance, if we take the diagram like this, the field, and we apply GR, well, as the solution is like, well, when it starts, yeah, of course it exists and so on. However, the question is only about the density of the field. I mean, how will the densities? It will be connected with the couple sources?
No, excuse me. It's not a question. You write the equation, you solve the equation, and you see what the equation tells you. And it's not that you can impose to have a very weak field. I mean, that string solution, general relativity bosons, has some started. And without imposing, but looking at the configuration to be stable, what do you think, Shishan?
Follow discussion.
Well, analytically we cannot solve, like, let's say, to my knowledge, at least any configuration where we have the defect NGR. Numerically, there was numerical level 2019 and quite recently simulation where they put this Lagrangian, they put the full jar with a mesh refinement in Cambridge, and they did some simulation in Cambridge. Paul Shalad.
Yes.
And
it would be good if you give us the reference.
yeah, I can give you, and they consider the different string tension, and they, for instance, they were considering the loop that shrinks, and when it collapses, it forms a black hole. And they consider the full jar, the simulation.
Well,
That's also because you need this for gravitational wave stochastic regard.
Yes, but
what are you saying?
You need this calculation to estimate the stochastic regard of gravitational wave simulation. But also before, maybe Carlos was
No, just a moment. Let's not mix. I mean, the background gravitational wave is a problem by itself. What I'm saying here, to study that solution, which formula called, that is a very clean problem to be checked and to study, which has nothing to do with the otherwise we go back to legal and so on. This is crazy. I mean, this is absurd. We need to do physics here, like I looked at many years ago. We need to do physics and to see what happens. I will be happy to look at that paper and give you a point. Looking myself. But I think that is the way, independently of what we cannot be any longer guided by the algorithm. We cannot be part of the propaganda. We are physicists. And this problem is a well-defined physical process. Namely, could this system with this field, with that amplitude, become unstable and form black holes? And what is the size of this problem? We are working on this topic also continuously. And we have seen, indeed, that the system of self-gravitating Fermi, not portions, self-gravitating Fermions, can form stable configuration. You know what is it? This is a fantastic solution. If we learn so much for the Fermi, there is much more to learn on this kind of thing. And again, don't tell me that we have to look a LIGO, we are going to find a jet in the galactic center. Yes, the Nobel Prize winner said he was looking for a jet in the galactic center. Yes, we have data of that. And right now, question of 1 month, it has been proved that cannot rotate. You understand the paradox? I mean, he takes that he expects to be a Kerr solution with spin. No, the spin. No, he used this word of God last thing. Disco. Disco is my word. And without knowing that was my work, he mentioned ISCO. Now we write a mail to him. But apart from that, already now this crazy work has been dismantled. There is no rotation. Dismantled. I hope you realize. Therefore, we keep working with not many people, but with many good ideas. And when you are here, you can also ask to see the GRP result of today, which are really incredible. And you all, and also you should study the result of GRP today, of day and year, where you are here. But you have to study and appreciate. Otherwise you are losing time, opportunity. Okay, I think this is as much as I
Yes, I think we're very happy to scientific exchange after so long time, so we could continue, but question time is limited, so.
Yes, but in the meantime,
yes,
in these 2 years, we have been able, like I said in Pop-up, to think about it and to work a lot. I realized that Newton was able to write the Principia only because there had been a plague. And he wrote the Principia during the plague. I mean, this article which is coming out, when it's coming out, the article is at 29 of September.
26, I think he said.
Eh?
26, I heard.
Which one?
26, yours,
Which paper?
the GRB one.
No. Oh, yes.
26.
29.
Oh.
But anyway, whatever it is not yet out, but it will be soon out. And that again, it took more than 2 years to fix it.
Okay.
Good.
And bring the paper
Yes.
of this week back to Portugal
Okay.
with you.
I will not go to Portugal. Anyway.
Excuse me?
I will not go to Portugal from here.
Where we go?
I will go to Belarus for now.
To?
To Belarus, to Minsk, for a while. Just for vacation. So then I will come to Portugal.
Then we will go
Then
back.
I will go to Portugal.
Yes, definitely. And you can stay in touch. You're to the center of the
Yes, yes, I will update you about it. Okay.
Thank you.